Alright, so we'll just do some quick questions on atomic structure just to understand, just to test your understanding so far and what you know about it. So the question says complete the following sentences concerning the energy level diagram for the hydrogen atom. Okay, so we know what hydrogen is on the periodic table, and of course, we understand that hydrogen, we're working with a single energy level, right? With one electron. That's what hydrogen is. Okay, with a nucleus with protons that is just a single proton as well. Okay, now let's answer the questions. The energy levels in the hydrogen atom get closer as n does what? Okay, so in any atom that you're going to picture, the basically what we are told is that's the first energy level, um, and then that's the second energy level. Let me do something that is like this, and then so as you tends to go away from the nucleus, so as n increases, what's going to start happening will be the energy levels will be getting closer and closer. So I find that the ones that are closest to the nucleus are not as close as compared to the ones as you go outwards. Okay, so basically that's what's happening. So the energy levels in the hydrogen atom get closer as n increases. Of course, n represents the energy level. The one closest to the nucleus is the first one. So they get closer as the n increases. B. When n is equal to infinity, the energy separation of an electron from the nucleus is equal to the dash. When n is equal to infinity, the energy separation of an electron from the nucleus is equal to what? Okay, so basically what we're trying to say is when you've got an electron and then it's transitioning or it's being separated from the nucleus, when n is equal to infinity, the energy separation of an electron from the nucleus is equal to 1. So the separation of this electron from the nucleus away from that first energy level going up to n is equal to infinity. That's what we're trying to talk about here. What's the energy? The energy is equal to what? So basically when n is equal to infinity, that implies you've permanently disconnected or removed that electron. You've completely separated it from what? From the nucleus. It is not on the energy levels that can be numbered, so it's basically just disconnected, and so that becomes the ionization energy. Okay, the amount of energy required to separate an electron from the nucleus completely. Okay, so that's B. C, the equation relating and I think maybe just on B, just a quick note that I just need to make is the energy of an electron. Maybe this equation you've never come across it. The energy of an electron on each energy level is given by this formula. Okay, that's in electronic volts and then n squared. The n on the bottom represents a principal quantum number. Of course, as you go over some other questions, you understand what the principal quantum number is. This principal quantum number represents the size and the energy of the energy level. So if it's on the first energy level, it will be n is equal to 1. So this is a formula that gives you how much of energy is an electron possessing at the level at which it is. And then C, the equation relating the separation between the levels in the hydrogen atom to the number of the level n is called the dash equation. So we're trying to look for an equation that is relating the energy, okay, separation between the levels in the hydrogen atom. So basically what you're trying to picture here is where you have something like this. Okay, so n final 1 over n initial squared. Okay, so energy separation, so the formula is going to be change in energy is equal to negative 13.6. Okay, so this equation is called the Liedberg equation, and I know some of you may not understand how it comes about. So this equation relates the energy separation. What is the energy difference as electrons transition? This is the final, that is the initial. Okay, so how does this equation come about? Now, some of you already know that you've already come across the energy is given by Planck's constant multiplied by frequency there. This equation can be expanded as h. We know the frequency is inversely proportional to the wavelength. Okay, this is one equation, and then we know that the original form of the Liebig equation is 1 over the wavelength being equal to Liebig's constant open brackets 1 over n final squared minus initial squared. Okay, now if you get the first equation, well, we are saying energy is equal to hc over wavelength, and then you you decide to divide both sides by hc. What you are going to end up will be something like the energy is going to be over hc is equal to 1 over wavelength. Okay, and then this part which is having 1 over the wavelength, you can substitute that part, and that is energy over hc, right? And then you can multiply both sides by Planck's constant and the speed of light. Okay, so on the left is just going to disappear. Now Planck's constant, which is 6.6 times 10 to the power negative 84, multiplied by speed of light 3 times 10 to the power 8, and multiplied by Liebig's constant. This is what will give you now what you were seeing in electron volts. Of course, it depends. If it's in joules, it will be something like 2.18 times 10 to the power negative 18. But then if it's in electron volts, it will be equivalent to negative 13.6 electronic volts. So this equation is what relates now the change in energy as an electron transitions from one energy level to the other. Okay, so that's it to these simple questions. Alright, so question 2 now. Briefly describe the following: Bohr's model, postulates and its limitations, and then with particle duality. So we'll start with the postulates before we look at the limitations. So Bohr's model and then postulates. Okay, so what did this guy actually say? What did he tell us according to his model? Okay, that's what we're starting with. So number one of the postulates of Bohr is in an atom, electrons revolve around a positively charged nucleus. That's number one. So electrons revolve around the nucleus. Okay, so I've put it in a full form. Electrons which are negatively charged, of course, revolve around the positively charged nucleus in a definite circular path called shells. So that's one of the postulates. That's why when we're drawing an atom, we've got the nucleus inside, and then we tend to put the shells around. And then the first postulate is these electrons revolve around in the shells. Okay. Number two, the other postulate of Bohr, it says each orbit or a shell has a fixed energy. So we represent these energies, of course, using the integers. So each orbit has a fixed energy. So each shell has fixed energy. Okay, that's why we call them energy levels. Okay, they are known as orbital shaped shells or energy levels. Number three, the energy levels are represented by integers. Okay, so that's why we say n is equal to 1, n is equal to 2. Okay, so the energy levels are represented by integers known as the quantum numbers. Okay, so, and then the other thing that is also important is the orbits are assigned K, L, M, N shapes, shells. So K, L, M,
N is also another way of representing these shells. And then the other postulate of Bohr is the electrons in an atom move from a lower energy level to a higher energy level by gaining, and from a higher one to a lower one by losing. Okay, so electrons move to higher energy levels by what? They do that by gaining. And then, so what that means is if we are moving from n is equal to 1 going outwards, electrons supposed to gain, and then as you drop, supposed to lose. So these are the few postulates that you need to take note of Bohr's model. And then we can just look at the limitations of this model. Okay, so what were the limitations? So Bohr's model failed to explain the Zeeman effect. So failed to explain Zeeman's effect. So Zeeman effect. So this is an effect of a magnetic field on the spectra of atoms. So Bohr failed to explain that. And then his model also failed to explain the Stark effect. Okay, so this is an effect of an electric field on the spectra of atoms. He couldn't explain. And then it violates the Heisenberg uncertainty principle. Okay, violates Heisenberg uncertainty principle. And then the last one, it could not explain the spectra obtained. So could not explain the spectra obtained from larger atoms. Okay, so these were basically the postulates and limitations of Bohr's model of an atom. And then let's end with B and just look at the wave particle duality. So this is just an argument that when you look at an atom, okay, which is of course we can call it a quantum entity. So quantum entities, in this case specifically an atom, exhibit particle or wave properties. So quantum entities exhibit both. So we've seen a particle, both particle and wave properties. This is what wave particle duality tells us, and this is where we get this equation. Is this when determining the wavelength, and then Planck's constant over this. This is where this equation comes from. Okay, comes from wave particle duality. That's an argument that was basically made. So every particle quantity can be described as either a particle or a wave. Of course, as a particle, we talk about it in terms of mass, and then as a wave, we talk about the wavelength. That's why this equation combines mass and wavelength together. Okay. Okay, so we have question 3. We need to determine the wave number and frequency of infrared radiation having the wavelength of 3,500 angstrom. Okay, so angstrom may be new to you, okay, but one thing that you need to know is one angstrom is actually equal to like 0.1 nanometers. So you can see that angstrom is actually smaller than a nanometer. Okay, so we already know that. So if that is the case, we know nano is 10 to the power negative 9, so 0.1 times 10 to the power negative 9 meters. So that is just 1 times 10 to the power negative 10 meters. So 1 angstrom therefore is equal to 1 times 10 to the power negative 9 meters. So we can easily convert our given value to meters. can just multiply, okay, and find the value of x there. So end up multiplying 3500 by 10 to the power negative 9. So what I'm getting is 3.5 times 10 to the power negative 6 meters. So that is basically the reason why we use these expressions like angstrom, nanometers, is to represent these values that are smaller better. Okay, so our goal is to determine the wave number and the frequency of that radiation. So what we have, so we've been given the wavelength, so the wave number, which we can denote like this, v with a bar on top, is just 1 over the wavelength. That's all. So the value we have, 3.5 times 10 to the power negative 6. Okay, you can divide that into that to get the wave number. How many waves do we have? So 1 divided by that answer, so we have 2.857 times 10 to the power 5. Okay, so that is our wave number. And then what else do we need to determine? We need to determine the frequency. So what equation relates the frequency and the wavelength? So the equation that does that is frequency is equal to the speed of light over the wavelength. Speed of light is 3 times 10 to the power 8 over the wavelength 3.5 times 10 to the power negative 6. So grab your calculator there. 3 times 10 to the power 8 divided by 3 times 10 to the power negative 6. So I'm getting something like 1 times 10 to the power 14 is. Okay, so we've answered question 3. Let's answer now question 4. The blue color of the sky results from the scattering of sunlight by air molecules. Blue light has a frequency of 7.5 times 10 to the power 14 is. Calculate the energy of a single photon associated with this energy. So we've been given the frequency. One thing that's very important from the first part of the question. So the energy of the photon is given by E is equal to hv. Okay, so in this equation, the h we have is called Planck's constant, and v is representing the frequency. So for us to determine the energy of a photon, we're going to use this very equation. So therefore, our energy is equal to Planck's constant is 6.626 times 10 to the power negative 34, and then multiply by the frequency, which is 7.5 times 10 to the power 14. Okay, so we're going to have energy of a photon in joules. So 6.626 times 10 to the power negative 34 multiplied by 7.5 times 10 to the power 14. So the value is 4.9695 times 10 to the power negative 19. That is joules. So for the sake of our final answer, we'll take it to two significant figures. So approximately that can be 5 times 10 to the power negative 19 joules. So that's the energy of a photon. Now B says calculate the energy of a mole of photons with this energy. So whenever you're dealing with moles, this is where now the issue of, let me bring back that. So this is where the issue of the Avogadro's constant comes in. So in this case, we know Avogadro's constant is 6.022 times 10 to the power 23. So in this case, since we're dealing with photons, we'll say photons, and the units are always going to be per mole. So if you're dealing with atoms, molecules, it's always that same value per mole. Now I want to determine the energy. Okay, so we know that this is joule per photon, right? So I'll use the actual value, the one that's not rounded off, 4.9695 times 10 to the power negative 19 joules per photon, which is our solution to the first part. So that multiplied by 6.022 by 10 to the power 23. So here the value becomes 2.99 times 10 to the power negative 5. That is joules per mole. So we've determined now the energy per mole. But by the way, that's not the power negative, it's a positive value. So if we take that to kilojoules, we can divide by 1000. So dividing by 1000, the value we have is 299.2 kilojoules per mole. Okay, and then C says, would the energy be sufficient to break the... So by the way, it's not a mass that you need to convert to kilojoules per mole. You can leave it here, it's still fine. But I've converted it because I wanted to compare it to this. So the question says, would the energy be sufficient to break the chlorine to chlorine bond? So the amount of energy required to break the bond of chlorine to chlorine is given to be 242. So since we have 299 kilojoules, so that's enough, right? So here the comment we're making is, yes, it is sufficient, since the energy determined there is what? Is greater than the enthalpy required, the enthalpy of the chlorine to chlorine bond. The speed of an electron is 1.68 times 10 to the power 8 meters per second. What is the wavelength? So we're looking for an equation that would relate the speed or the velocity to the wavelength. So that is what we call de Broglie wavelength, which comes from the wave-particle duality. So the equation is Planck's constant over the product of your mass and your velocity. Okay? So we need to have a value of Planck's constant. It's going to be very useful. So our wavelength becomes, Planck's constant is, let me use this part, Planck's constant is 6.626 times 10 to the power negative 34 over the mass. Are we given the mass in this case? So the mass is not given, so we're going to use the mass of an electron instead. Okay, so the mass of an electron is a constant, so multiply by the velocity, which is 1.68 times 10 to the power 8. Okay, so mass of an electron. So the mass of an electron is 9.109 times 10 to the power negative 81. Okay, so that's the mass of an electron. So with what we have there, let's basically get to divide. So I'll start with the denominator. So the 9.109 times 10 to the power 81, that's of course in kilograms. So 9.109 times 10 to the power negative 81, and then multiply by 1.68 times 10 to the power 8. So the value I'm getting for the bottom part is 1.530312 times 10 to the power negative 22. and then we can divide that value, so I can actually substitute it. So 1.530312 times 10 to the power negative 22. So you can divide that into the Avogadro's, or sorry, into the Planck's constant. So 6.626 times 10 to the power negative 34 divided by that there. So the final answer, which represents the wavelength, is 4.3298 times 10 to the power negative 12. Okay, so since all our units were in their standard form, we can take our wavelength to be in meters, since we use kilograms. So that is meters. So if you want to take it to nanometers, you can multiply by 10 to the power 9. So the power 9, that gives me 0.0043298 nanometers. You can decide to move a decimal place 1, 2, 3, so that we have 4.3298 times 10 to the power negative 3 nanometers. So that's a wavelength. And then we now need to determine the wavelength for the transition from n is equal to 4 to n is equal to 2. So the equation that we use there is the Liebig constant equation. Okay, so it's the inverse of the wavelength being equal to the Liebig's constant, and then for the transition we show 1 over final energy level minus 1 over the initial. So it doesn't matter what you start with, you don't have to worry yourself about being able to remember that. What matters is your final answer should always be a positive. That's why you can see in certain textbooks you may have a negative in front of the Liebig's constant. That is just to counter remove the negative that may come out from the inside there. Okay, so let's approach it now. So what's the value of the Liebig's constant? So Liebig's constant is 109,677.57 centimeters negative. So we can take it to meters. Okay, so how do we do that? We know that 1 meter is equal to how many centimeters? It's equal to 100 centimeters. So we can divide the 100 centimeters into that value. So thus we expect the decimal point to move how many times? 2 times, right? So 1 and 2. So we have 109. Immediately we're going to have something like 1,000. So we have 1,096.7757 meters negative. Okay, so we can now substitute to get the wavelength. So 1 over wavelength, so we have 1 over wavelength is equal to, what do we have there? So Liebig's constant 1096.7757 meters negative, and then you can open the brackets, 1 over the final in this case is 2, so 2 squared minus the initial, which was 4, so 4 squared. So for such questions, start with what is in the brackets. So 2 squared is 4, 4 squared is 16, right? So I have 16 there. So let's just simplify whatever is on the right hand side, and then you can just deal with the inverse of that, the reciprocal. So 1 over 4 minus 1 over 16. So that gives me 3 over 16. So 3 over 16. 3 over 16 multiplied by 1096.7757. So this gives 205.645 meters negative. So this is equal to 1 over the wavelength. So for us to determine the wavelength, if we cross and multiply, in short, if we multiply both sides by the wavelength, what are we going to have? So wavelength. So the wavelength will be on the right hand side, and so be required to be divided by 205 into the 1. So 1 divided by 205.645 meters negative. So the answer I'm getting is 0.004862738. So that is in meters. So if you want, you can take it to nanometers by multiplying by 10 to the power 9, which becomes a value that's too big. So we can take it to centimeters. How do you take it to centimeters? We know a meter is equal to 100 centimeters. So we can multiply it by 100. If we multiply by 100, we have something like 0.486 centimeters. Okay, that's still fine. We can still understand that value. And then we can move to a second part of the question, which says state the name given to this spectroscopic series to which this transition belongs. State the name given to the spectroscopic series to which this transition belongs. So whenever you are having a transition to the second energy level, we call it Balmer series. Okay. Transition associated to the first, we call it Lyman series. Okay. And then for the third energy level, pass chain, to the fourth, it's called bracket. And then for the fifth one, number 5, we call it p-fund. Okay. So the Lyman is associated with UV, that is N is equal to 1, ultraviolet. And then for the Balmer series, that is visible light, okay, on the spectrum. And then for the other 3, infrared is associated with them. Okay. Alright, so path chain, that is N is equal to 3, bracket is N is equal to 4, and then N is equal to 5 is the p-fund.